When I was doing my undergraduate education in mechanical engineering, I was very fascinated by fluid mechanics. Air and water are fluids and they flow with a very complex pattern in the environment, and I was drawn to apply this knowledge of fluid mechanics to environmental problems. The aim of this project is to study three aspects: energy, water, and carbon in the environment of Princeton. Locally, we would like our sensing technologies and our models to be combined to make our buildings smarter and more energy efficient. The idea of these meteorological stations is that you want to build them as cheaply and simply as possible. And currently we have about 12 stations around the Princeton campus, and we are looking to increase this to 20 or 30 stations. These are computer model outputs of the surface temperature over Princeton. What we see is first Lake Carnegie, which is hotter than the Earth's surface during the night and cooler during the day. And if you look at the Earth's surface, you will see that the vegetated parts are always cooler than the built terrain or the buildings. If we keep zooming down, we can get to the level of one individual building. We can then simulate the airflow around this building and observe how the presence of this building will create a lot of turbulence around it, which means a lot of mixing of pollutants and heat and other things in built terrain. We went out looking for some gas sensors that we can connect to our sensor network to get concentrations of carbon dioxide, but we did not find any that fit our need. Gerard Wysocki and I decided to develop high-quality sensors that are low power and that are essentially customized to work with our wireless sensor network. Just like we can model differences in surface temperature because of differences in surface types, we can also go out and measure these differences with a thermal camera. An urban planner, for example, might wonder whether it's better for Princeton to have a green roof or to paint our roofs in white if we wanted to reduce the cooling loads and the heating loads of the campus. What this wireless sensor network will be able to give us with all the nodes or sensing points that it has, it will be able to tell us what is the difference between surface temperature and air temperature on a roof or in a street. What's the difference between a vegetated grass surface and a concrete or an asphalt surface? And with that, we can essentially know if we increase the vegetated fraction or the vegetated cover in a suburban area, how will that affect evaporation and how will that affect the urban heat island that will be produced by this area. Global climate models will tell you what's happening at a very large scale. What we try to do is downscale these climate predictions to the local level. So we want to see how a small city will respond to a climate change given by these global climate models. The wonderful thing about academia is that you wake up in the morning and you go to work knowing that today you will learn something new, or you might even discover something completely fascinating every day.